So we're going to real quickly talk about molecular structures. Okay, so we're going to list the basic steps used to draw Lewis structures. So I kind of went over that a little bit in the last video, but we'll go into more depth how to choose which type of Lewis dot structure to start with, etc. We're also going to look at resonance and what that is, and you should be able to identify when resonance structures exist. And then we'll talk about a few exceptions to the octet rule. So really a structural formula and resonance. Those are the new vocab terms. And so the main idea, structural formulas show the relative position of atoms within a molecule. So it's kind of like a Lewis dot structure, but instead we're also focused on what are the bond types, what do they look like. And there's sometimes more than one way of showing how electrons could be arranged in molecules. That's where we'll get to resonance structures. Okay, so these are the basic steps to drawing a Lewis structure. So the first thing you want to do is predict the location of atoms, right? Is there a central atom? A central atom is going to be the atom that the most things will bond around, right? So in methane, CH3, the central atom would be carbon because CH4, because carbon is going to have 4 single covalent bonds that it wants to form with those hydrogens, and so they're going to form all around the outside. So we call them terminal atoms, and we call the center ones, the carbon, a central atom. So it's always important to figure out what that central atom is. If there's a group 14 element, it's going to be the group 14 element. If there's a group 15 but no group 14, then group 15 will be the central atom. And you can kind of continue on the further away you get, right? Once you get to just having group 17 elements, the halogens, and or something like hydrogen, you won't have a central atom. In those cases, when you have two atoms bonded together, you'll just have 2 atoms. There's not a central or terminal atom, and so it's okay. You don't have to worry. They're going to form a linear atom, and so linear molecule. So we don't need to have a central or terminal atom. Okay. Once you've figured out central and terminal, okay, determine the number of electrons available total. So carbon's got 4 electrons, right? Valence electrons. And then each of the hydrogens has 1. So 4 plus 4 is 8. Okay? Divide that number by 2. You get 4. So there's 4 electron pairs that you can work with, right? Well, if I want my central atom to get to 8 valence electrons, well, if I just put each of those 2 around the outside of my carbon, my central atom, guess what? Carbon's happy. And then I just have to put my hydrogens on each of those spots where there's a pair that I've created, and guess what? Each of the hydrogens are happy, right? Doesn't always work that nicely, but that's the general gist of it, okay? There'll be times where you'll have all of your terminal atoms will end up needing 8 also, right? And so then you have to work a little differently. We'll talk about that. But so once you've figured that out, then you place those bonding pairs. Then you can determine the number of electron pairs remaining after you've put a bonding pair around the central atom, right? If the central atom isn't happy, if the central atom's happy, but your terminal atoms are not with their total number of electrons, that's when you can start thinking about, do I need a double bond between the central atom and one of these terminal atoms? Do I need a double bond between each of the terminal atoms and the central atom? Whatever makes it work overall, but you can't have, this is key, you can't have more electrons than you should be having or starting with because of your total number that you could get from all the terminal atoms and the central atom. Okay? So here's some other, just a shorter form too of what I just mentioned. Not always perfect, so that's why I had to go through a little more in depth before, but this is just in case you want to kind of go through this, right? But there are some that do not need to have 8, right? So specifically hydrogen, helium, lithium, and beryllium are all, well, helium's not going to form bonds because it's a noble gas and already has an octet. Well, not an octet, but a duet. Lithium and beryllium are metals, so they're not going to form covalent bonds, right? Boron's one of those other non-metals in a certain sense that we could talk about, but don't worry too much about it. So let's look at what a structural formula is, right? So if you remember chemical formula, that tells you how many of each element are present. So in CO2, you know there's one carbon, and you know there's two oxygens because the subscript 2 represents that there's 2 of the element right before it, which is oxygen. A structural formula uses letter symbols, and bonds to show relative position. So it's kind of like a it's kind of like a Lewis dot structure, but you show the bonds and relative positions of each of the atoms and how they would form that bond, right? So let's look at 2 examples. An example would be acetone. Okay, so there's a carbon here. There's a double bond right here between the carbon and the oxygen, and there's single bonds here between these carbons and these outer carbons, right? These 3 hydrogens here technically would be coming off in the same angle or degree of angle that on each side. They just are abbreviating it here. Okay. One thing to note is that here I have 2 lines, here I have 1 line and 1 line. We'll get to that in a second. Another example of a structural formula is water right here. Okay, you have 1 line and 1 line off of the hydrogen representing the bonds between the oxygens and the hydrogens. Now you see that they're angled, they're not just straight out, and that's because these molecules are not going to form just straight structures. Okay, they're going to have elements bonded at angles because of what we'll get to in the next section, talking about VSEPR theory, which is valence shell, electron pair repulsion, right? They want to repel, they want to be away from each other. They don't like each other. So electrons are going to do that. Okay. So when we're drawing structural formulas, lines represent the type of bond. So a single line is a single bond, 2 lines is going to be a double bond, and 3 lines is a triple bond. What do you know? Okay. So what type of bonds does this molecule have? If you said single bonds, you're right. Okay. What about this molecule? What type of bonds does it have? How many bonds does it have? So what type? It has double bonds, right? And it has 2 double bonds. Okay, now let's look at the term resonance. So resonance is a condition that occurs when more than one valid Lewis structure can be written for a molecule or ion. So an example is a benzene ring. This is a really great one for organic chemistry. We're not going to go into it too much. I just want you to kind of get the idea. So see how here I have a double, double, and a double. Over here I have a double, double, and double here. Okay, so basically what that's saying is that those double bonds, we can't really determine exactly which part of this ring of, these are all carbons that are bonded together. We don't know exactly where the double bond is, and in fact in nature, it's not something we can kind of identify exactly where the bond is because the electrons are always moving and they're being shared, and so it just wants to be happy, and so it actually almost all the time seems to be forming a double bond all the way around, but that's really just because in nature it's all about being perfect and being happy, and it'll do whatever it can to be stable. But in reality, the electrons, there are not enough for a double bond all the way around. There's a double bond here, double bond here, double bond here, or here, here, here. So it's 2 forms of drawing this validly. That's basically what a resonance is. There's more than one form of drawing a valid structural formula, a valid Lewis dot structure. Okay. So when the molecule behaves as though it has only one structure, though, but has multiple abilities to be drawn, that's resonance. Okay. And the bond lengths are going to be identical, even though a double bond, if you remember from last section, a double bond would be shorter, right, than a single bond. But they're relatively going to be the same because in nature, like I said, they move so fast that it's almost like it's just one thing. Okay. An example here is nitrate. This is a polyatomic ion, and you can see here that they've drawn in the in this structural formula a single line and then a dotted line, kind of representing that this could be drawn as a double bond here and a single bond here and a single bond here, or it could be a double bond here, single bond here, single bond here. So essentially, to have all the electrons being fulfilled at all times, you're going to have movement of these electrons, and you're not always going to have a double bond on each one, or just one here, or one here, or one here. It's not stuck. and that will end that section.